Alright, hello everyone. We are going to be continuing our problem on projectile motion. Now we are going to consider a situation with linear drag. This is a continuation of the problem that you've seen in part 1. Okay, so from part 1, here is what we found out. Okay, so from part 1, of the same problem, okay, we came up with the following figure, which if you remember, I don't want to paste it as an image, but well, I guess, right? So if you remember, this is the situation that we came up with. Okay, so after going through the basic motions of the problem, so after looking at where the receiver was at time t of 2.5 seconds, we found out, okay, that person has run a distance of 75 feet, and we need to do several things which are the same as what we were expected to do in the previous problem. But what's different from this problem? So in this problem, okay, so in this problem, we need to find the same things. Okay, find v naught, theta naught, find v peak, time taken to reach t peak, and I know the location of the peak point, location of the peak point in the x and the y directions, but in the presence of acceleration due to gravity, and also in the presence of linear drag. Okay, so in this problem we have two terms contributing to acceleration due to gravity and also linear drag. Okay, and here is what I'm going to do in terms of the acceleration expression. So this will be given to you here. So you are told that the acceleration vector is going to be some minus c times the velocity vector minus g times j. Okay, so where, if you notice, the minus c times the velocity vector is from linear drag. Okay, and the value of this constant c is also given to us in this problem as 0.35, and then so use c is equal to 0.35. Okay, so this is the problem that we need to solve. All right, so I'm going to start looking at this problem from scratch in terms of the equations that we need. Okay, so basically the first step is the equations of projectile motion in the presence of drag. Okay, so how do we come up with these equations? That's the first step. Once we have the equations, then it's just a question of substitution. Okay, the basic ideas remain the same as in the previous problem. All right, I'm going to start off by looking at the acceleration vector. So this is minus c times v minus g times j, which can be written as minus c times vxi minus c times vyj minus g times j. This is because v is vxi vyj. Okay, which means that the acceleration vector can be written as minus c times vx in the I direction and minus c times vy minus g in the j direction, which tells me that if I equate this entire thing as axi and ayj, then ax is equal to c times vx, and then ay is minus c times vy minus g. Okay, so this is in the presence of drag. Okay, and you can compare it with the absence of drag. In the absence of drag, compare. In the absence of drag, you would have had ax is equal to 0 and ay would have been minus g. Alright, so once we have this idea, then all I'm going to do is the following. Okay, start off with ax is minus c times vx, but by definition this is dvx by dt. Okay, which means that I can say dvx by dt is minus c times vx, and so I'm going to bring the vx down here, and then this is going to be minus c times dt. Okay, which means that if I do the integration on both sides, starting from some initial velocity to some velocity in the x direction, this is going to be from initial time 0 to some time t. Okay, so I'm going to assume t naught is equal to 0. Okay, all right. I'm going to skip the integration of all of these because I expect that you'll be able to know it, or in the worst case you can always go ahead and look at Wolfram and so on. So this is going to be logarithm of vx from vx naught to vx, and this is going to be minus c times t minus 0. Okay, or if I do the substitutions, I will end up getting vx is equal to vx naught, let me write that clearly. So this is vx naught times e to the power minus ct. Okay, so this is the expression for velocity in the presence of linear drag. Okay, I'm sorry, and I'm putting a box around this because these are all fairly important equations, and I want to do that for these guys as well. Okay, the acceleration guys as well. All right, so what we have to do is we have to do something similar in the y direction. Okay, so which means that I take the y component of the acceleration. Ay is minus c vy minus g. This is by definition dvy by dt. Okay, which means that dvy by dt is minus c vy minus g. Here is what I'm going to do. I'm going to write this as the following. dvy by dt is minus c times vy plus g by c, just taking a common factor of that out. Okay, and if that is the case, then I can write the integral now in the following manner. So this is dvy, there is a function of vy there, so I have to bring that on to the bottom here. G by c, this is equal to minus c dt. Integrate it from vy naught to some vy. Integrate this from 0 to t. I'm putting the details of these integrations on my elaborate notes on this particular problem, so I'm going to skip the details of the integration. Okay, so look at the details. So details of integration posted on my elaborate notes. Okay, so I'm skipping all that, and if you go ahead and do some mathematical gymnastics, then you will end up getting vy is equal to minus g by c plus vy naught plus g by c times e to the power minus ct. So this is getting complicated, as you can see, right? This is not a piece of cake. Almost there. All we have to do is do the same thing for the position, and then we are good to go. All right, now I'm going to go to the next one. Okay, we know that vx is dx by dt, and we also know that vx is vx naught e to the power minus ct is dx by dt. So I take the like-minded powers of these like-minded terms of these quantities, and then I distribute them. So I say that, okay, dx is vx naught dt, integrate it from some x naught to x, integrate this from some 0 to t, okay, because I'm assuming t naught to be 0, okay. And then if I do the integration, I end up getting x is equal to x naught plus vx naught by c times 1 minus e to the power minus ct. And typically, you know, if these are all things that you may or perhaps be given in an exam, or I might actually have you do these step by step, and please make sure that you know how to do these kinds of basic integration ideas, okay. Once again, the details of the integration, I want to make sure that you understand the details. I'm just skipping them here because we want to save some time on these problems, okay. All right, I want to bring it back to the same color. All right, then last one is a slightly more tricky customer, okay. We're going to have vy is dy by dt, which tells me that vy, which was that huge thing that I had there, so that's minus g by c plus vy naught plus g by c times e to the power minus ct. All of this is equal to dy by dt, which means that dy is equal to minus g by c dt plus vy naught plus g by c minus ct dt. I'm just breaking it up into two pieces. Integrate this from y naught to some y, integrate this from 0 to t, integrate that from 0 to t. Skipping the details of the integration, this is fairly straightforward, as you will see, okay. And I get y is equal to y naught minus gt by c. That's a fairly straightforward integration there. And then I'm going to have vy naught plus g by c divided by a factor of c, all of it, times 1 minus e to the power minus ct. The factor of 1 comes because of the fact that the time t naught is equal to 0 to begin with, okay. And so I have all the equations for the case of linear drag, okay. You can club them all and write them on the same page if necessary, okay. But here are all the equations, okay. So for linear drag, for projectile motion with linear drag starting at t naught is equal to 0. Here are the equations that I have. I'm just going to bring them all down here, okay, so that we all have them in the same place. All right, I'm going to start with the acceleration, guys, okay. So these are two things that I need. I'll copy that and then bring it down here, sorry, okay. So that's one thing. Then I have the velocity equations as well that I need to bring out, okay. So here is the velocity in one direction, the x component of the velocity, okay. And then I also have the y component of the velocity, this big guy here, okay. And maybe I'll just write it down underneath there. And lastly, I have the x and the y components of the displacements, okay, or the distance traveled in the x direction and the y direction, okay. And here is the distance traveled in the y direction. All right, so these are fairly important equations, as you can see. I just want to shift this down to a better spot here. Okay, the derivations are not too bad. They're fairly straightforward as well, as long as you do the basic integration steps. Okay, and so with all these equations, then all we have to do is that just start doing it the same way as before. Okay, so now I go back to our figure from before. Okay, so this is the situation that we have from before. I guess I have low battery, but I'm going to ring it and see how far I can get along. Okay, so I have my figure from here. I'm going to paste that. Okay, the basic ideas are the same as before. Okay, to find v naught and theta naught. Okay, I make use of the fact that x naught is equal to 0, y naught is equal to 7 feet, and then x at 2.5 seconds is 165 feet, y at 2.5 seconds is 6 feet. Okay, and then I substitute. Okay, so substitute into the x of t and y of t equations. Okay, and this is at t is equal to 0 and t is equal to 2.5 seconds. So if I do that, here is what I end up getting. Okay, so x at 2.5 is x naught plus v naught cos theta naught by this constant factor of c, 1 minus e to the power c times t. Okay, that's at 2.5 seconds. Okay, then I also have y at 2.5 is y naught, and then I'm going to have the rest of the big guns minus g times t 2.5 by c plus v naught sine theta naught plus g by c divided by c times 1 minus e to the power minus c t at 2.5 seconds. Okay, substitute x at 2.5, y at 2.5, x naught, y naught, t at 2.5 is 2.5 seconds, c is 0.35, this is given. Okay, and then g is 32 feet per second square. Okay, and then if I solve from this one, the first one and the second one, we end up with v naught cos theta naught is equal to 99.1 feet per second. Okay, from 2 I end up with v naught sine theta naught is equal to 45.22 okay feet per second, which means that I can solve for theta naught, and I end up getting theta naught to be as 24.5 degrees. This is a little shallower than what we had for no drag. Okay, likewise v naught in the case is going to be a little faster. Okay, this is going to be 109 feet per second, because you have to throw it faster to reach the same distance in the presence of drag, as opposed to the case of no drag. Okay, so that's the reason for why the speed is a little higher. Now I'm going to go to find the peak time. Okay, that's something that we had to find out as well, right? To find the peak time, we make use of the same ideas from part 1. Okay, from part 1 of the problem. What is that idea? Velocity at the peak, I can write it as some x peak in the I and then y peak in the j direction. but I know that velocity y peak is equal to 0, okay, and velocity at x peak is not 0, okay. So I make use of the fact that the peak velocity is only in the x direction. So take a look at Vy peak at t is equal to t peak. Okay, if I look at the basic expression for Vy, here is what I end up having, right? So Vy was minus g by c plus v naught sine theta naught plus g by c e to the power minus ct, which means Vy peak is minus g by c v naught sine theta naught plus g by c t peak. But I know that Vy is 0 because of that particular fact, okay, because of that particular fact, which means that I can solve for t peak. Okay, if I do the solution for t peak, then I get 0 is equal to minus g by c v naught cos theta naught g by c times t peak, or I can say that e to the power minus c times t peak. If I rearrange the furniture, this is going to be g by c, all of that divided by v naught cos theta naught plus g by c, okay. And essentially you can take logarithms on both sides, take natural log on both sides, okay, and then solve to get t peak is equal to 1.148 seconds. Okay, so that's the answer for t peak. And once I have t peak, then I can calculate the velocity at the peak. Okay, so this means that velocity at the peak, which is equal to x peak, is vx naught e to the power minus c times t peak, which is v naught cos theta naught c times t peak. Okay, substitute. I'm going to have v naught as before. Okay, we had solved for v naught as 109 feet per second. Theta naught was 24.5 degrees, and then t peak was 1.148 seconds, and so the velocity at the peak point is given as the following. Velocity at the peak is going to be 66.31 feet per second. Alright, and the very last thing in this problem is to calculate the location of the peak. Okay, calculate the location of the peak. Calculate location of the peak point, which is x peak, y peak. The same idea as before. Okay, so same idea as part 1 of the problem. Okay, nothing different here. All I do is I make use of the x and the y equations. Okay, so x peak is x naught, and then this is going to be v naught cos theta naught divided by a factor of c times 1 minus e to the power minus c times t peak. And the important thing is c is given to us as 0.35. Okay, and likewise y peak, we have the expression for that as y naught minus g by c times t peak, and then this is going to be v naught sine theta naught plus g by c all of that divided by this factor of c times 1 minus e to the power minus c t peak. Okay, substitute. X naught is 0, y naught is 7 feet. V naught we know from before, 109. Theta naught was around 24.1 degrees. C was 0.35. T peak was 1.148 seconds. And then G was 32 feet per second square. Okay, and if you do all the substitutions, then you'll end up getting Y peak is equal to 31.2 feet and X peak is likewise 93.7 feet. Alright, so not much of a difference between what we did in the past and what we're doing now, except that in this case we have a situation of linear drag, and in the previous case we had a situation of no drag. And if I just quickly plot the trajectories, okay, so with and without drag. Okay, here is how they would look like. Okay, here is my x-axis and here is my y-axis. Okay, I'm plotting the trajectory without drag first. Okay, so that goes up and then comes down and lands at a height of around 6 feet. Okay, so this was initially 7 feet. And this height here is 6 feet. Okay, and then the peak point was somewhere here in the case of no drag. And then in the case of drag, the idea is that the peak has been shifted a little bit. Okay, the peak has been shifted a little bit, and the particle is traveling this way. So the peak point, this is P1, this is P2. This is the situation with drag. Okay, and the dotted lines represent the situation without drag. And if I were to mark these distances, as you can see them here, okay, the peak has been shifted by a little bit. Alright, so this distance here was 81.2 feet from the previous problem, from part 1. Okay, and then the new distance that you're going to have here is this guy, which is slightly longer, so that's around 93.7 feet. Alright, so this is the situation with drag and without drag, and you'll also see that the initial angle is a little shallow for the case of the drag, okay, as opposed to the case of no drag. And if I remember right, the case of no drag, the initial angle was approximately, I'm finding that out as 31 degrees. So if I do that here, okay, very last thing, this angle here was around 31 degrees, and now the new angle is around 24 degrees. Okay, so this is without a drag, and this is with drag, and this is the V0 and the V0. So the V0 is slightly higher but shallower with drag. V0 was slightly steeper but less shallower in the absence of drag. All right, thank you so much for your patience. We were able to complete this problem. I appreciate your time. Stay safe, and I'll hopefully see you in the next concept talk. All right, bye bye.